Hi, today we are going to take a look at this vintage indicator. This one is a total air temperature and rated EPR indicator. This device was manufactured in 1985. There are several quality stamps here. So this thing was manufactured by Siemens Precision. So there is a part number. And there is also a part number from TWA. On the rear there is a typical circular connector. On the front there is a test button, a 3-digit indicator for total air temperature and EPR, and here 4 annunciators, difficult to read. First we will see the internal construction, and after that I will try to make it work, probably after a reverse engineering, which can be complicated for this one. Okay, look at that. This is the 4 boards construction. Okay, so we can see several CMOS logic ICs here. So we have 3 4511. These are BCD27 segments decoders. 3 of them because we have 3 digits here. So this is a display board. And we have here several transistors. This permits to drive the luminescent displays here. They are called the Minitron KW105S. So here we have LM124. This is a common quad op-amp. So here I cannot read 4081. This one is not common. This is a dual D flip-flop 4013. There is a small transformer. Another power supply transformer is here actually. Okay, we can see the very nice construction. The 4 boards are interconnected using this flat flex interconnection, and we have only 5 wires between the rear assembly here and the front assembly. Let's have a look at the other boards. We have seen this one. The second board is mainly a digital board. There are several logic ICs. On that area there is an analog section. You can see this nice capacitor. Seems to be a Mica capacitor. An op-amp, a classic 741, a few transistors. On the third board there is here the driver for the second display, a quad comparator, and here several logic ICs. This part is a 10 kHz oscillator. Okay, here a power transistor or voltage regulator maybe. The last board contains only analog parts. There are very accurate resistors here, 0.2% for this one. And there are several op-amps here, 714, 101, large capacitor, 3 microfarads. Here we have a quad op-amp, another one here, and other accurate resistors. For the reverse engineering, I have attached these 4 boards in order to have something rigid. This is the first step of the reverse engineering. I have started with this board here. Each part is placed on this drawing using an appropriate symbol. Okay, for example, the N-channel JFET, a quad op-amp, transistors, diode, and so on. This is the second step of the reverse engineering. It was not obvious. The routing is far from perfect. You can see, for example, these 2 resistors here, which permit current bias compensation. You can see that they are connected to the op-amp here, non-inverting input, this one and the other one here. So the best solution would be to place these 2 resistors close to the op-amps. When the routing is not perfect like this one, it is more difficult to do the reverse engineering. We can see here the front end for the total air temperature measurement. Obviously the input is here. We have here a differential amplifier. The output is fed to this inverting amplifier. There is a bias adjustment here and a gain adjustment. You can see that we have here 2 resistors connected to a voltage reference, and we have here a trimmer and another resistor. If you are familiar with analog designs, you can figure out what is this circuit here. So let's see a second schematic with a new arrangement. We have here a new schematic which is actually identical to the previous one. Okay, so we have here actually a Wheatstone bridge, and here we have a PT500, a platinum sensor, 500 ohms at 0 degree. The connection is done using 3 wires. These 3 resistors RS modelize the cable from the indicator to the total air temperature probe. These 3 resistors are identical. The return point is here. It is connected to this voltage divider. We will see in one moment why we have this voltage divider. So you can see that the left leg is here, this resistor, this parasitic resistance, and the platinum sensor. The right leg is here. So we have the same parasitic resistance, and we have the trimmer and this resistor. So therefore, if we suppose that the current which flows through this leg is identical to the current flowing through the other leg, in that case, a change of the resistance Rs has no effect on the differential voltage here. So therefore, we have a compensation of the series resistance of the cable. So now this circuit is not perfect. First, this resistor is not completely linear with temperature. At the output here, there is a negative voltage, and the absolute value of this voltage increases with temperature. So therefore, this voltage decreases when the temperature increases. So this permits to have a larger power supply when the temperature increases. This permits to correct the nonlinearity of the bridge due to the platinum sensor and also due to the bridge configuration here. So this is the rest of the circuit of the analog board. This circuit is a part of the ADC. There is actually an integrator. And this signal is connected to the logic of the ADC. We have here 3 switches. This one permits to connect the input of the integrator here to a reference voltage through this resistor. There is a second switch which permits a voltage measurement. So this is, I guess, the EPR input of this indicator. And we have a third input here which permits the measurement of the total air temperature. This line is connected to the previous amplifier. Here we have a voltage corresponding to the temperature. This voltage can be positive or negative. And here we have a circuit which is actually an absolute value circuit. If we suppose that the voltage is negative at the input here, at the output the voltage will be positive. Therefore the diode will be forward biased. And therefore we have here an inverting amplifier. The gain is -1, so this transistor is off because this voltage will be approximately 0.7 volt above the emitter voltage. Now, if we consider a positive voltage, in that case the output will be negative, therefore the diode is off. At the output there will be a voltage close to the negative power supply rail. Okay, but this transistor will be on, and this transistor provides a short circuit between the input and the output here. Okay, so therefore the gain is +1. That line is connected probably to a comparator. So this line permits to activate the negative sign of the display. The ADC permits only a measurement of positive voltages. For the test, I will use this precision resistor decade box from Burster, model 1424. Accuracy is 0.01%, and the resistance is very stable, below 1 ppm per degree. So first, let's have a look inside this unit. As you can see, this thing is very heavy. You can see the rotary switches here. You can see also that each rotary switch is associated with a stepper motor. You can see also the quality of the contact here. It is of course possible to connect this unit to a computer in order to set the resistance. This unit has an HPIB interface. For the test, I have connected the probe input of this unit to this resistor decade box which simulates the total air temperature probe, which is the platinum sensor, 500 ohms. So we can see that for 500 ohms there is a temperature of 1 degree. We can perform a display test first. On that table there is the correspondence between the resistance and the temperature. There is also the sensitivity. We can see that the sensitivity decreases with temperature here. There is approximately a variation of 5% between minus 80 to plus 80 degrees. Let's start with this resistance, 362. Okay, minus 69 instead of minus 70. Next value is 382 ohms for minus 60, 402, 421, 441, 461, 480, 519, 539, 558, 578, 597, 616, 635. Okay, so let's see the maximum temperature. 77, 78. And minus 77, 78. It is symmetrical. I didn't succeed to activate the EPR mode. There is maybe an issue with the electronics. I will continue the reverse engineering for 1 day approximately, and I will see if I can make it work. That's all for this indicator. Thank you for watching and see you next time for another video. Bye bye.